Hello, my name is Guilherme Pote. It is a pleasure to introduce our work entitled Extracting Deformation-Aware Local Features by Learning to Deform. Our work is about learning deformation-aware local key point description on still images. The paradigm of detecting and describing sparse key points is still the de facto approach adopted in tasks such as image-based 3D localization and mapping due to its computational efficiency and repeatability of matches. In this context, local features are used to match unique corresponding points across images that observe the same scene. However, in general, local descriptors assume that each key point undergoes an affine transformation between frames. This assumption is broken when substantial viewpoint changes happen, such in this example. Beyond that, another challenging transformation that can occur is a non-rigid deformation. Dealing with non-rigid transformations is even more difficult than projective ones due to its high degree of freedom and nonlinear changes in the local appearance of an object. Our world is not only composed of rigid bodies. People, animals, and clothes are typical examples of deformable objects that often appear in front of the cameras. Here we track a point on a deforming surface and extract a local Cartesian patch to demonstrate the impact of deformations on methods based on local patches. We can observe that even locally, the deformation can change the appearance of the image patch significantly. Non-rigid tracking and reconstruction are tasks that can directly profit from methods that robustly handle correspondences of surfaces under deformation. According to the literature and our experimental evaluation, three methods for extracting local features from images stand out. The hard-net approach uses a VGG-like network architecture and an in-batch hard-negative mining strategy during training. Log-Polar proposed to improve hard-net by using a polar sampling instead of the Cartesian approach when sampling the local image patch, attaining increased robustness to local affine transformations such as scale and rotation. Differently from the other methods, GeoBit proposed to perform the sampling of the local patch based on surface geodesics, an intrinsic object property that can be extracted from RGBD images and is invariant to isometric deformations. In this table, we show the advantages and drawbacks of each of these methods. Log-Polar and hard-net are fairly robust to affine transformations but are sensitive to non-rigid deformations. On the other hand, GeoBit can handle both affine and non-rigid transformations. Still, it requires depth information, which is not always available. In contrast, our deformation-aware local descriptor, which we name DEAL, only relies on RGB images and can deal with both affine and non-rigid deformations efficiently, as we demonstrated in our experiments. Our network learns how to deform the input image patch during training with a carefully designed spatial transformer. At inference time, our network applies the learned deformations to the local patches before extracting the features, aiming to maximize the similarity of corresponding descriptors. Our proposed deformation-aware network architecture takes as input an RGB image plus a set of detected key points. A ResNet34 head is used to extract mid-level features from the input image by reducing its spatial dimensions and increasing the number of channels. After extracting mid-level image features, the first spatial transformer block is used to obtain a local 5x5 tensor from the feature map at the position of each key point. This local tensor encodes mid-level semantics such as local shape and texture that can be used by the thin plate splines regressor. In our network, we model the local deformations via a thin plate splines transformation, which is fully differentiable. In short, a TPS transformation can be described by the control points, which is obtained by the initial affine transformation from key point attributes, and transformation parameters. The TPS regressor is a multi-layer perceptron that regresses the parameters of a local deformation. We use a polar transformer to initialize a polar grid according to the key point attributes. The identity polar grid and the TPS parameters are used to apply the local deformation to the identity grid. This whole selected block composes the second spatial transformer of our network. After applying the estimated deformation, we resample patches from the image to account for image deformations. Finally, the rectified patches are propagated to HardNet, which extracts a compact and distinct local descriptor. The network is trained in a Siamese fashion, where two networks with shared weights are used to extract the local features from corresponding key points from a labeled dataset. To optimize the network, we employ the hardest unbatched triplet loss, enforcing the network to jointly learn meaningful deformation parameters and distinctive features. To evaluate our method and the compared baselines, we rely on publicly available RGBD datasets of non-rigid objects. The considered datasets contain 11 real-world and 3 synthetic objects with accurate landmarks. A photometrically optimized TPS model for dense correspondence of each image pair is also provided in these datasets. Here are some examples of the deformations present in the sequences. We also consider in our evaluation the deformable surface tracking datasets. These additional sequences contain ambiguous textures and highly repetitive structures besides deformations. We train our network on a simulated dataset containing about 20 million SIFT correspondences obtained using the simulation's ground truth. It is important to mention that the 3 synthetic objects from the evaluation benchmark were never used during training. The textures from the simulation are real images obtained from large-scale structures from motion datasets. We trained the network for 10 epochs, using a batch size of 8 image pairs, each pair containing up to 128 correspondences. We use the matching scores as the primary metric to evaluate the descriptors. The matching scores is given by the number of correct matches divided by the minimum number of detected key points between the reference and target frame. The mean matching accuracy is the percentage of correct matches of co-visible key points in the image pair. It is worth mentioning that all key point attributes are shared among all local descriptors, and we detect at most 2048 SIFT key points for each frame. To match the descriptors, we use brute force nearest neighbor search. We compare our methods to the traditional descriptors daisy, orb, and freak, in addition to the deformation and light invariant descriptor DALI. We also consider the RGBD methods brand that computes geometric and photometric properties, and GeoBit, which is invariant to isometric deformation of surfaces. Concerning the learning-based RGB methods for local features, we consider TFEAT, LogPolar, and SOSNet. Finally, for a comprehensive evaluation, we additionally consider the joint detection and description methods. Those additional results can be checked in our paper. In this table, we evaluate all local descriptors using the same set of SIFT key points. First of all, we observe that brand, an RGBD method that computes geometric and texture features simultaneously, achieves the worst results. This happens because brand was designed to work with rigid scenes and is doubly penalized when both geometry and texture are deformed. DALI, a descriptor that handles deformation with 3D shape analysis of a local intensity patch converted to a mesh, achieves the best results among the handcrafted descriptors. The LogPolar descriptor demonstrates increased robustness to deformations among the learned descriptors, due to its sampling strategy robust to local transformations. GeoBit, for its turn, achieves the second best performance using RGBD images. It uses geodesics extracted from geometry to compute in isometric invariant descriptors. Finally, our method obtains the best performances across all datasets. Since our network is trained end-to-end, it is able to learn deformations that maximize distinctiveness of the descriptors. In the rotation plus deformation experiments, our method also achieves the best performance among all local descriptors using the same set of key points. While in the scale plus deformation invariance, our method is competitive with GeoBit. Worth mentioning is that GeoBit uses additional depth information. We conducted a time performance analysis among the deformation-aware descriptors for extracting 250 descriptors from standard definition resolution images. Our method outperforms GeoBit and DALI by a large margin, since they are only capable of running on CPU. We also check how the training data and network components affect the performance of the descriptor when dealing with deformations. We evaluate the performance of each configuration in the synthetic scale sequences which have the most challenging deformations. In the first experiment, we replaced the polar transformer with the standard Cartesian sampling, which gives the worst results. Then we train our full model with planar transformations only. It achieves similar accuracy when compared to using the polar transformer without the non-rigid warper trained with deformations. This indicates that our proposed non-rigid training dataset can be used to improve existing methods like log-polar. Finally, the full network achieves the best results when training the entire deformation-aware network with the proposed dataset of synthetic objects, meaning that our non-rigid warper can further increase the descriptor's robustness to deformations. Additional experiments on a dataset of planar scenes H-patches are available in our supplementary material. In addition to the standard metrics, we evaluated descriptors in two practical applications, non-rigid object retrieval and non-rigid tracking. We also include in the comparisons the state-of-the-art descriptor for image retrieval DELF. DELF uses its own detected 2048 key points optimized for retrieval. In the image retrieval task, given the reference image of a deformable object, the descriptors are used to search images of that object in a large database. In the first example, our method is competitive to DELF, a descriptor optimized for retrieval. And in the second qualitative example, our method is able to outperform DELF and all other methods. In this graph, we showed the average accuracy achieved when querying all reference images and retrieving the top K object matches. Our method outperforms all methods in terms of retrieval accuracy when considering the top 12 objects or less, and is competitive to DELF when considering more objects. We also evaluated the descriptors for non-rigid tracking of surfaces. Given a reference image, we detect shift key points independently in both reference and target frame, match them using the descriptors, and then estimate a TPS warp using RANSAC. The warp is used to rectify the deformed object back to the original template. We compare the methods using the number of n-layers from RANSAC and the learned perceptual patch similarity, or LPIPS for short. Our method DEAL obtains the highest n-layer count alongside GeoBit and is competitive in terms of reconstruction of the template. Some qualitative results from the reconstruction of the templates are shown below. The reconstruction using the n-layers from RANSAC, hence the similar scores for all methods in LPIPS score. In this work, we proposed a deformation-aware architecture that can be optimized end-to-end. We also create a synthetic dataset with realistic non-rigid deformations and textures, suitable for training deep networks. The source code and training data is available at our website. Thank you for watching. You can obtain the source code and datasets by scanning the QR code.